Okay, good afternoon. Thanks to the organizers for the kind invitation. So I will present recent results from the Tevatron, and for that I would like to thank my CDF and D0 colleagues, since all these results have been produced by the two collaborations. So there have been many presentations in the prior sessions, and you can see here the list of this presentation. They are sorted out in 4 big categories, and I will follow this order. I will talk about QCD, then a bit of new phenomena and big quark physics, top quark physics, and electrodynamics to finish. Most of the results are recent and based on the full Tevatron Run 2 dataset, and I will not have much time to go into the details of the results, but you can find them in these presentations. So before going to the results, let me remind you some unique features of the Tevatron, which have been also mentioned by the previous speaker, is that, of course, we have a different collision energy, but the main point is that we have PP bar instead of PP, and this translates in the asymmetries, for instance, either in the top or in the electroweak. This gives us a much better sensitivity for a given amount of luminosity and statistics. And here you see the example of the top quark forward-backward asymmetry that I will discuss. There is another important aspect, is the initial CP invariant state, which also has features which can be exploited in B physics. And there is complementary processes, different mix of QQ bar versus glue-glue collisions, and this makes a difference in TT bar spin correlations. We have a well-understood detector, and this shows that indeed we can do precise measurements of W and boson and top quark mass. And at this moment I will switch, because I think this is the PDF. It's not high quality. I'll switch to this one. Okay, so let's go now to QCD. So for the hard QCD aspect, we have completed the program successfully on alpha S and jet-based in general, and we are now concentrating on Z plus jet and W plus jet cross-section measurements. And here you see, for instance, 2 examples of the PT of the Z differential cross-section of the Z plus jet, good agreement with the most modern calculations. Here I have W plus jet with a delta phi between the jets, so we have many of these studies now performed on large data sets, and these are all show good description with NLO QCD. We are pushing towards heavy flavor plus Z or W. Here you have an example of Z plus charm jets, differential cross-section. Here we saw some discrepancy, and indeed we understood that we had to indeed boost a bit the gluon to CC bar content in the simulation to have a better description of that. But in general, we have good description of these distributions. We have also performed exclusive interesting results with W or Z plus D star, fully reconstructed, and this give access to low PT of the charm. And here again, nice differential distribution as a function of the PT of the D star, which is well described by the predictions. In soft QCD, we have also an extensive program we are completing now. We have exclusive production that I will not talk about either for lack of time. I will concentrate rather on double partner interactions. And you see that double partner interaction are schematized here, where indeed 2 partons take place into the collision, into the event. And this is important because this happens, in fact, more often than one could think naively. And when you can deduce from the cross-section of the double partner that you measure, you can deduce an effective cross-section based on the process which takes place from the two double partner interaction, and gives you some information about the uniform or clumpiness of the distribution of the partons. So depending on how you measure this sigma effective or not, you see that. So we have measured the fraction of double parton in gamma plus 2 jets in PT beams, and this varies from 12% at about 17 GeV to down to 2% at 27. If you do that in gamma plus 3 jets, you have also the same strong variation from 47% to 23% in the same GeV range. And if you look at effective cross-sections, you see also that you can get to nice precision, consistent with previous results, and actually the most precise presently. We have also recently observed double J-type events at the Tevatron. The measured cross-section is given here, and the dP fraction in these events is also quite sizable at the level of about 30%. So for physics beyond the standard model, as you know, since 1992, we have a very strong claim that 400 physicists failed to find supersymmetry, and we are proud to update this thing with 1,000 physicists at the end of run 2 of the Tevatron. And I think at this conference, there are 6,000 physicists who also failed to find supersymmetry. But in fact, the problem is that there is not so much better whole, although we have looked in many of this exotic physics, but no signal has been observed. And in fact, this is realm of LHC. There are still a few holes for the Tevatron, and we are including searches also in B or top physics, as I will say. So regarding direct search for new phenomena, Tevatron is competitive for low mass search, typically about 500 GeV. And so we have a recent results on W prime and Z prime, which may appear in BSM theories, and these decay to TB bar or TT bar. These events are generally triggered by the W decaying leptonically. So the new limits that are shown here are the world's best at intermediate mass, typically between 200 and 700 GeV, and then indeed the limits from LHC takes over. So the Tevatron program on direct search for new phenomena is essentially complete with about 200 papers. A few more results will appear in the next year, but we are basically now looking for new phenomena in other areas. So one of the points which has been with us since some time at T0 is an excess asymmetry in the like sign Dimuon production. And unfortunately, it's the only experiment which can make this precise measurement because of it has the magnet reversal polarities capabilities, which reduce the systematics, and it has a CP invariant initial state. So there has been several measurements which we have performed over the years, and they all tend to give this minus 0.3% asymmetry, while this is theoretically well calculated to about an order of magnitude smaller. And it's not a problem of statistics because this is an inclusive measurement, and the known source of CP violations are clear, and so we can calculate this thing precisely. So the last word on this has been done by releasing the 10.4 inverse femtobarn, and you have a strong cross-check with the inclusive muon asymmetry, which you see is in perfect agreement with the standard model, while again, the Dimuon asymmetry is clearly offset, and if you compute now, we are at 3.6 standard deviation from the standard model prediction, so the puzzle is unresolved, and unfortunately, we have no more data to check that. We can interpret that in a CP violation framework, and here you can then deduce the ADSL and ASSL. You see here the measurement, the distance to the standard model, and nevertheless, you can derive these quantities, and these are in fact the world burst asymmetries, while delta gamma D over gamma D has now been, there is a better measurement from LHCb on this one. So the deviation from the standard model is sensitive to the value of the gamma D over gamma D. This is what we realized in this analysis, and we need maybe more input on these quantities to see what's going on. Another puzzle has been the forward-backward asymmetry in the TT bar system, and so for that we went into the BB bar and looked for it and see if we could see the same effect. So there have been two analyses just released, one by CDF at large BB bar invariant mass. Here we use BB bar pair using jet triggered data and jet charge to identify the B from the B bar. This is done in bins of the invariant BB bar mass, and this is low statistics because you go at high mass, but it's in the same regime as the TT bar asymmetry. You see that the data are consistent with zero asymmetry, while the axigluon models would be clearly away, and in fact, some of them are excluded in this analysis. So this is one point. The other point is at low mass. This is a new method, tagging directly a B plus, B minus production, so you can know if it's forward or backward. And here again, the analysis lead to zero asymmetry. As you can see here, the exact value is minus 0.3%. The prediction is about 1 to 2%. We don't know the systematic uncertainty yet on this value, but you see that these numbers are consistent with zero, and basically we don't see anomaly in the BB production. So in TT bar, what is the status? Let me introduce the point by reminding you that there are two asymmetries that one can look, the real TT bar forward-backward asymmetry in which you reconstruct both T and T bar, and the leptonic one in which you just use the lepton of one of the decaying top. And these two quantities are correlated, but they have different systematics, so it's interesting to look at them simultaneously. And that's what we have done. And in fact, the situation has been confused until 2011. I mean, this was the situation. We had the low asymmetry at the level of 4%, while what we were measuring was between 15 to 20%. And so definitely we needed to put the whole statistics inside. And we also improved the analysis, for instance, by using lepton plus 3 jet events, which were quite useful. So when we did that, this is the situation now. The leptonic asymmetry, you see that D0 in good agreement with the prediction. CDF has a very slight excess, so we can see that in the leptonic asymmetry there is no issue. In the TT bar asymmetry, one can note also that the prediction has slightly increased because of higher order correction and also electroweak correction, which has been included. And the full data set has brought our data a little bit down, so basically this is also compatibility with standard model. And finally, the kinematic dependence, which was also quite tantalizing, in CDF is still visible. In D0, you have a point here, so basically the two things, when you look at the two results together, you don't see such a big discrepancy anymore. So we are working now on the CDF D0 combination of these results to give the final answer, but you can guess from this plot that we don't see so much of an effect. Top pair cross-section, I will not go very long on this one because I have a long talk, so just suffice to say that you have 5% precision on the combined top production cross-section, and we are doing studies on differential cross-section as a function of PT, MTT bar, rapidity, as shown here, and in general, we have good description by the MCAT law and approximative law. Moving on to single top production, as you know, this process contains three components: T-channel, S-channel, associated production. The single top production has been observed in 2009 by CDF and D0. Then we went through T-channel observation. Recently, TW channel was also observed at LHC. And what about S-channel, which is the most difficult, and why? Well, it has low cross-section, but at LHC it's particularly challenging because it's only this green part of the pie, while at Tevatron it's pretty big, and so indeed you have a chance to look into that. And this is important because indeed, besides the fact that you can do electroweak physics, like determining VTB independently, going to the B quark and PDFs, you can also make constraint on anomalous couplings, polarization, and CP violation. So we want to have these things measured properly. And these are the two extraction by CDF and D0. You see these two plots are consistent. The S channel is here, the T channel is there. We have determined VTB at the level of 9% precision. So this is now beaten by LHC, but it's still quite nice to see that we have the approach by the two channel, and this is important because the new physics which could appear in these things do not appear necessarily in one channel or in the, can appear in one channel or in the other, so we need to constrain this cross-section properly. In S-channel, we have then combined the signals that CDF and D0, which had about 3.5 sigma each, so you see here the compatibility between these results. And when we combine the individual discriminant, we get to this super discriminant here, and you see that the data clearly prefer this light blue, which is the S-channel. And when you do that, you have a 6 sigma observed significance with a cross-section of 1.29 plus about 20% error, which is consistent with the standard model prediction. And this, in fact, was nice because we saw publication of the two collaboration, which led to the observation of a new process. Moving on to the top mass, this is another important point for the Tevatron. Here you see you have in general the best channel is the lepton plus jet. In the hadronic case, you can make use of the QQ bar of the W and then make an in situ calibration. This is pretty powerful and is done in all analysis nowadays. And what is interesting is that 3 new Tevatron top quark mass measurements have been produced since the last top world mass average, which was only last spring, and which was giving 173.3 GeV. So we have a CDF dilepton template method with 9 inverse femtobarn, an all jet template method with 9.3, and the recent 9.7 inverse femtobarn, which has been recently accepted by PRL, and since it's the most precise, I will spend one slide on it. So this one is based on the matrix element technique. So here we calculate the event probability on an event-by-event basis. And the advantage is that you are using the 4 vectors with this, all the kinematic and topological information. So it's very good in terms of statistical power, especially at the Tevatron where we have less statistics than at LHC. The disadvantage is this high computational demand, but this has been indeed solved in this iteration of the analysis. We gain a lot in terms of computing, and so we were able really to reduce significantly the systematic uncertainties which are dominated by AMC statistics. So basically, we went from an error of 1 GV with the 3.5 inverse symptom analysis to 0.5 GV. So the new measurement is 175 GV plus or minus about 0.7 GV. This is the most precise measurement currently across the accelerators. This is the new Tevatron top mass combination released today for the conference. We have put best results of each experiment in each channels, run 1 and run 2. So we have new L plus jet and these 2 CDF measurements, as we just said. All correlation are taken into account. Here you can see the agreement across channels. You see that indeed no outliers are there. Here you see channel really channeled up by here. It was by decay channel. Here is really by channel by experiment. Again, no outliers, and the result is now 174.34. So it's exactly 1 GV higher than the world mass combination. And this now top mass is known with 0.37% precision. So this is a 26% improvement compared to our previous Tevatron combination. So it's very nice, and so we look forward to more combinations with LHC results. Note, since we were talking about this phase diagram of the standard model this morning, that we are moving decisively into metastability. We are going from here to here. And although we are not sure we are talking about the top pole mass here, the uncertainty is still at the level of about 1 GV between top pole mass and Monte Carlo mass, so we are still really difficult to get out of this region. Electroweak, we just heard about this aspect in the previous talk, but I will just briefly summarize what we did. So we have an updated lepton charge asymmetry. From 7, we went to this 9.7 inverse femtobarn. Again, we have make a significant gain in precision and in the eta coverage. So this is the most precise measurement of lepton charge asymmetry to date. You see here the comparison with the PDFs. We pushed this analysis, making use of the missing E2 to make W boson production asymmetry extraction. And the potential, so you see here this measurement. You see here the ratio. You see that indeed NNPDF and MC10O plus NNPDF gives a good description. This is the red one, while other ones like old PDF are clearly ruled out. And so there is a potential improvement of PDF models in the XQ² region of interest for the W production that we are doing at the Tevatron, and this will reduce by approximately 30% our error on the PDF down to 2-3 MeV, so this is quite crucial, as we will see later. Sin squared theta W and W mass indirectly has been also covered somewhat before. I will just here so then focus on the important points regarding the Tevatron. So first of all, we know the tension that exists with previous measurements, and so it's important for us to be able to see if we can reach such precision. And in fact, that's exactly what we are doing. With the current measurement, we are able to reach the best world precision at these hadron colliders, and now our precision goes down to 47, 10 to the minus 3, 10 to the minus 4 actually. And so if you compare now this measurement, this is the point here, you see that indeed we lay in between the two discrepant measurements, and the LEP SLD average is a pretty good prediction for us. And besides, you see the CDF and measurement at 9 and 2 inverse femtobarn. And as the previous speaker was mentioning, the EE measurement is soon available in full statistics, and so it will be pretty nice to combine all these results afterwards. When you do the extraction of the W of MW from these measurements, you get to a pretty nice precision already with these two measurements at the level of 45 MeV. And when you combine CDF and D0, we really should be competitive with the best W mass measurements indirectly. The W mass direct measurement has also been previously reported, but let me remind you that indeed we are dominating this field at the moment with a 16 MeV error. This is to be compared here. You can see the lab measurement before, which was the best before Tevatron got so precise. The full data now is being analyzed, and we hope to have a significant reduction of uncertainties. We have a statistics gain, which will gain us, of course, precision in the energy scale uncertainty, since we use Z to make calibrations. And also we are going to extend to forward leptons at D0, and so again, with the PDF improvements that we were mentioning, we should get some significant gain. We are targeting 10 MeV world average with the new CDF and D0 measurement using the full statistics, and this we hope to have it within the coming year. And when you do that, of course, you can do the consistency check of the top W and Higgs. So regarding the Higgs, I will just, since we are talking about celebration, it's nice for us also, we are going to soon celebrate 2 years of evidence of fermionic decays at the Tevatron, because indeed we published on 27 July 2012 the evidence that we had at that time with the cross-section. And this is about a cross-section which was a bit higher than the standard model. In fact, it's interesting to see what's the current best measurement of the cross-section. You see that the Tevatron is 1.6 plus or minus 0.7 times the standard model, while CMS is bang on with plus or minus 0.5, while Atlas, we are waiting for the final update of this, the latest update with the full statistics, but so far it was measuring pretty low. So in fact, these numbers show clear differences, and it would be nice to combine them, especially that the expected sensitivity for all these results is pretty low, and in fact, even by combining them, we are not able to make observations, so it will take some time to observe this process properly, probably the full run of the LHC. Besides, I will just remind that we had final combination of all these channels. The measured mu is consistent with the standard model. The process, the mu for each process is also consistent. We did some extraction of the couplings, which of course have not the same precision than LHC, but this has been completed. What is new and what is going on is the Higgs spin and parity studies at the Tevatron, and this is different because, in fact, since we use the BB bar system, we can use associated production, and here we are not going to use angular variables to do that. We are going to use threshold effects, which are very different depending if you have a 0 plus, a 0 minus, or a 2 plus. So these vary with the velocity of the VH system near threshold, and very strongly beta cube or beta power fifth. And so this makes a difference in the distribution. So take an example here. This is the ZH to LLBV bar. While the standard model distribution would be here, the two abnormal JP assignment would give you this big tail. So you understand that clearly we have strong separation when you do this kind of analysis. And that's what we did. So basically, we have done, at the moment, only D0 has released these results. CDF is very close to releasing them. And even one experiment is competitive here. Here you see, so the two hypotheses you have tested. The standard model is this green one. The BSM, this is a pseudo-scalar Higgs, is here. The data prefer the standard model. And you are able to exclude the 0 minus and 2 plus model at 98, at 99% confidence level for one experiment. The expected exclusion is at the level of 3 sigma. So you understand that if you combine with CDF, we should be much stronger than that, close to 5 sigma probably. This approach has also a very good advantage that it's easy to study Higgs spin parity admixture, like if you have a 0 minus and 0 plus admixture. And that's what we have done. We have varied the fraction and scanned our data. And then you can see that indeed, you see here the result. The data tend to be a bit in excess. So the limit, you exclude fraction greater than 80% at 95% confidence level for the 0 minus and 67% for the 2 plus, but in fact the expected values are close to 50%. So it's something promising, which we look forward to see the combination very soon. And with this, I'm coming to my conclusion. So basically, the CDF D0 are producing competitive physics, as you saw, and we are publishing them at a strong rate. We have now published over 1,000 papers and graduated over 1,000 PhD students, and many of them joined the LHC collaborations, are here in this room as LHC representative. It's very nice to see them again. In the last 2 years, we had many success by focusing on legacy results. W and top mass, single top. The forward-backward asymmetry in TT bar is very close to be finalized. The Higgs to BB bar has been finalized in terms of cross-section, but we are still looking at the spin parity aspects. BB bar Dimuon asymmetry, unfortunately, we are not able to fully resolve the puzzle. It doesn't look like it's a CP violation effect, a standard one, but it's not, we need more data to know that. I didn't talk about heavy baryons, although we had very nice results. Hard and soft QCD, I gave you some overview, and electronic precision measurements are also now coming up as very, very interesting. So in the next year, we expect new exciting Tevatron results. So the final results in top quark and electroweak physics, the Tevatron combined Higgs spin parity, and the W mass combined measurements with about 10 MeV precision. Thank you.
Thanks a lot for this overview, and it's open for a couple of questions.
In the final combined results for the Higgs, can you tell what is the contribution from the fermionic decays alone?
On the last 3.0 sigma, you mean? I think you can look at the, unfortunately I dropped the table which gives the, but you see, I mean, BB bar is the one which has clearly the strongest contribution now. So I don't have the exact numeric number, but it's, I don't know, 70–80% of the excess. Yeah.
There's a question there.
Okay, so I already told to Demina, the standard model prediction for the top asymmetry was never as low as 4%. What you are doing in this plot is to compare a prediction in the laboratory frame with a measurements in the TT-bar race frame, namely in the delta Y variable. The prediction of the standard model in this TT-bar race frame was always 8%, and has not changed significantly in the last years because of radiative correlations or electroweak corrections. So please correct this little mistake.
Yeah, we have corrected the reference. I mean, I agree. I mean, you agree that we had an error on the parallel session, but I can show you we have corrected the, we are now referencing PRD, which is Rhinewater and Company, which was producing this prediction at that time. So this prediction is published and it's at the 4.8% level. But it's true that your prediction was indeed, I mean, there was a mix-up.
Okay, we will probably not sort that out here. So there's one last question.
What is the mass, the top mass? So at the level of accuracy you have now, what is the definition that you use? Is the pole mass or?
We would like to use the pole mass, but as you know, we are experimentalists and we are using the mass which is in the Monte Carlo. So we are relying on theorists at the moment to find out what's the relation between this mass and the top pole mass. Recently, the difference between the mass that you're estimating at the top pole mass was estimated to be between 0.5 and 1 GeV. That's why when I was showing that plot, I mean, you can maybe shift this thing by probably 1 GeV, plus or minus 1 GeV, but not more. But I mean, it's a theorist who have to give us this answer.
Thank you.
Okay, so we are right on time, and I thank the speakers for that.